Hey, my name is Christopher Dean from Seattle, Washington, and this is my experimental demonstration for Dr. Buckner's MAE ECE-535 course on design of electromechanical systems at North Carolina State University. Today I'm going to talk a little bit about Faraday's law of induction and how it applies to a very simple and practical home demonstration. In general, Faraday's law of induction states that an electrical potential can be induced into a conductor when that conductor is exposed to a magnetic field. Varying magnetic field. In practice, what he's saying is by controlling the relative motion of a permanent magnet and a conductor, we can then induce a voltage into that conductor. Now the concept of Faraday's law of induction is as simple as his equation, which states that the induced voltage into a conductor is the product of the number of turns in the conductor coil and the time rate of change of the magnetic flux. And what we can take away from that, a couple of important things. If you want to change the magnitude of the induced voltage, you simply need to change the number of coils or change that time rate of change of the magnetic flux, which basically translates to spinning the rotor faster, changing the speed of that rotor. If you want to change the direction of the induced voltage, you simply have to change the direction of the relative motion. So it's the rotor spinning one way, the voltage goes one way, rotor spins the other way, voltage is going to go the other way. If we take a step back, really the goal of implementing Faraday's law of induction is to capture as many of those magnetic flux lines as we can inside the conducting coil as the field's interface with the conductor. So as the permanent magnets rotate around and come in close contact with that conducting coil, the whole idea is by minimizing that gap between the two and orienting the coil properly, we can capture as many of those flux lines inside the coil as possible. And the coil, as Dr. Buckner talked about in his lectures, the coil will then cut those flux lines, and that cutting is what actually generates that induced voltage in the coil. So for this demonstration, I'll give you a quick rundown of some of the major components. The coil that we're using today is a 30 gauge copper coil, magnetic wire, with about 655 turns. And we're using 24 neodymium N48 magnets that are attached to the rear wheel here, equidistant radially around the wheel. So those powerful magnets certainly aren't going to be the weak link in this demonstration. The gap between the conductor and the magnets has been minimized to about 20 thousandths of an inch. That's about as close as I can get before things start blowing apart. So without further ado, I'm going to go ahead and hop on the bike here, and I guess I should note that the whole goal of this demonstration is going to be to generate enough induced voltage to light this massive power source here, this little red LED. So if we can get that thing to light up, then we did a good job. So I'm going to hop on the bike and see what we can do. Okay, I'm going to hop on the bike now, and with any luck, although we don't need it, it's science, we're going to see this red light, little LED here, light up as I pedal my heart out. Here we go. I'm done. Alright, so clearly Faraday's law of induction was demonstrated successfully. Hope you enjoyed the light show as much as I did. Probably left you thinking, gosh, it seemed like an awful lot of mechanical input for very little electrical output. Managed to intermittently illuminate an LED for several seconds. And that's true. The system that I have here is extremely inefficient. Certainly there's ample mechanical power input and a massive amount of magnetic flux to induce a lot more voltage than I did, which concludes that the copper coil is very much the weak link here. The 30 gauge copper that I use can only handle so much current, and once it kind of passes that threshold of efficiency, the copper just dumps all the energy off as heat. So in the future, a much more efficient and practical design, which I hope to develop eventually, would employ a much larger, more efficient conductor that can really harness all this mechanical energy in this massive electromagnetic field that we're generating with these 24 magnets. So I hope you enjoyed the demonstration. Thank you very much for your time. And to add a little element of danger, I understand this is not very dangerous. I understand I wasn't wearing a helmet. I did this entire demonstration, come here, within just a few feet of this vicious dog.